Okay, calculus folks, it is time to step away from all the sign analysis and all the minimums and maximums we've been looking at lately. Chapter 4 is about applications of differentiation and, doing curve analysis and optimization problems and stuff is not the only application of derivatives. So we're going to take a couple of sections here to step back and look at limits and look at how we can use what we've learned about derivatives to help us solve some limit problems. In particular, first we're going to spend a section talking about limits at infinity, for which we're actually not going to do any derivatives at all. And then we're going to take a section and look at something called L'Hopital's rule, which is a direct application of differentiation to solving limits. So first of all, section 4.5 is about limits at infinity. So all the limits we looked at back in chapter 2 were where x was approaching some finite value. But now we're going to look at what happens when x approaches infinity. So we're going to start with an example. Let's start with a really familiar example. F of x equals 1 over x. This is a very familiar function. So let's draw a picture of it. It looks like this, right? And then it looks like this. It's got this hyperbola. This is a hyperbola here, okay? And if we look at what's happening over here on the right, we see as x approaches infinity, okay, as x values get bigger and bigger, we're dividing by larger and larger numbers. So the output of the function, f of x, is approaching 0. And in particular, it approaches from the right, or from above, from the positive side, from larger and larger numbers, which is we see the curve coming down towards 0 from above. Okay, that's why I put the plus there. So we can write limit as x approaches infinity of the function 1 over x equals 0. Okay, so this is an example of a limit at infinity. Similarly, on the left-hand side over here, we have, as x approaches negative infinity, f of x is approaching 0 as well, but from the left. So we can write limit as x approaches negative infinity of 1 over x also equals 0. What's going on here is we have a horizontal asymptote. This horizontal line right here at y equals 0 is a horizontal asymptote. Okay, and that is something you would have learned about back in pre-calculus or college algebra. We learned about horizontal asymptotes. And it turns out you can define a horizontal asymptote in terms of limits. So really, every time you have a finite limit at infinity, like in this situation where the limit is 0 on both sides, anytime you have a limit at infinity, which gives you a finite number, you have a horizontal asymptote. So we can take as a definition the following. A horizontal asymptote is a line y equals L. Okay, a line with equation y equals L. That's a horizontal line, where L is a constant, for which the limit as x approaches infinity of the function f of x that you're dealing with equals L, or the limit as x approaches negative infinity of the function you're dealing with equals L, or both. Okay. In mathematics, if you say or, generally that is an inclusive or. So either you have a limit at infinity which is equal to L, or a limit at negative infinity which is equal to L. And if either one of those happens, then you can call y equals L a horizontal asymptote. So horizontal asymptotes, as you can see, are just defined as a finite value where you have a limit at infinity. Let's look at another example. Let's look at the function f of x equals cosine of x divided by x. I'm just going to specifically look at the part of this function where x is greater than 0. This function is not a familiar function, probably, but here's what it looks like. It looks kind of like a wave, but the amplitude of that wave is being scaled by like 1 over x. Okay, we're dividing it by x, and so as x gets bigger, we're dividing by bigger and bigger numbers, which means the amplitude will be getting smaller and smaller and smaller. So it kind of actually has sort of like a vertical asymptote over here, Then it comes down and has a relatively large amplitude, but that amplitude gradually gets smaller and smaller and smaller. And it goes like this. Let me draw some more of this here. There we go. And what's happening is, as x is approaching infinity, the cosine of x divided by x is approaching 0. Okay, it is approaching 0, but it's not approaching it from above or from below. It's oscillating side to side, yet the wave amplitudes are getting smaller and smaller and smaller. So overall, it's still all approaching 0. And so this line, y equals 0 right here, right along the x-axis here, for this function is also a horizontal asymptote, because it meets the definition. Okay, this is not a situation where you might expect to see an asymptote. Sorry, that's gross there, but you may have heard people claim in the past that a function should not cross over its own asymptote. That's true for some rational functions, but not all rational functions, and it's certainly not true for functions in general, because an example like this, this function crosses over its own horizontal asymptote infinitely many times. So if you've heard people say that in the past, then they were in fact lying to you, perhaps without knowing it. That's not called lying, I guess. That's just called being wrong. But yeah, that is an incorrect notion, which I hear sometimes. So this is an asymptote that we're familiar with. Here's another example of a horizontal asymptote that we're not as familiar with, but which meets the definition of a finite limit at infinity. So this is a sort of I'm introducing limits at infinity by relating them to this familiar idea of a horizontal asymptote. Now in the next few videos, we're going to establish some rules to work with, and then look at some really rigorous approaches to solving some limit problems where x approaches infinity.